My name is Robin Moffatt. I'm a developer advocate at Confluent, and I'm rather delighted to be here speaking at GOTOpia this morning. I want to talk about Apache Kafka. We're going to talk about why you even need Apache Kafka and the concepts behind it, so that we can understand exactly what you can use it for, what you perhaps shouldn't be using it for, and what it is outside, maybe some of the misconceptions that people have of it. So to understand Apache Kafka, we want to understand the reasoning for why do we even need this thing in the first place. And at the very heart of Apache Kafka is this concept of these things called events. Events are the building blocks for what's the data that we work with day to day in our jobs. We just don't always realize that they started life as events. We work with databases, we work with NoSQL stores, we work with other sources of data. A lot of these places where we keep data, that data started life as an event. And events are these magical things that occur unbounded over time, kind of like until the end of the world. And events tell us that something happened, and they tell us what happened. And if we think about the kind of data that we work with, we can think of plenty of examples of human-generated events. Someone walks into a shop and buys something, or probably nowadays they kind of click online and buy something, but you have an event. Something was bought. What was bought? What was its cost price? What was the model? And so on. Or we move some inventory around a warehouse. So you have the notification that something happened. There was stock movements. What happened? Well, what was the stock item? Where did it move from? Where did it move to? What was the reason for moving it? So we have these events, and these happen continually over time. So events actually let us start to model out what's happening within our businesses. Events aren't just limited to human-generated events, though. We have plenty of machine-generated events. We have events happening across our networks, like our firewalls and our switches and so on, are capturing events all the time. IoT devices are continually giving out readings about the temperature around us, or the light sensors, or all this other kind of stuff. And the applications that we build also generate events. A user did something and it threw an error. Well, there's your event. Something kind of an error happened is the notification. And what was the error? What was the stack trace? These are also events. So we have all of these events around us, and we can use these events to build very, very powerful applications. We can use them to drive things in our applications, or our applications respond to what happens. So we can make systems much more responsive to our users. We can use events to build up state and reproduce what happened at a particular time. So we can use them to connect our systems around our businesses. So using these events, we can do great things. But we need a way of actually being able to do them. We need a kind of a platform on which to do that. So let's think about how we can actually build that platform. Let's think about an event. How are we going to work with this particular event? Or as we will probably have lots of events, because these events are happening maybe like continually, like vast streams, maybe just like periodically, every few seconds, every few minutes, maybe every few days, but they're still events. So we have these events. And what is an event? Well, we said it's like it's a notification and it tells us what happened. But for now, let's say it's a key value pair. Okay, it's going to tell us there's your notification that the event actually happened, and the value, well, what happened? And that value could just be like a 0 or a 1. It could be like a hugely complex scheme with a massive payload within it. But it's a key value pair for now. Where are we going to keep our events? How do we actually capture them and deal with them? Well, here comes the most important kind of like building block of Apache Kafka, which is the log. Now, when I say a log, I don't mean like you can like log.txt or your log4j or that kind of thing, although those are actually kind of like a type of event capture things that we're doing anyway. Here we're talking about a log in a very specific way. The log is where we take our events and we append them over time. So as events are happening, they're appended to the log. So something happens, it gets written to the log. Something else happens, it gets written to the log. And this log is immutable. So Kafka gives us some very, very powerful guarantees when we're building our systems. And here's the first one. It is that guarantees that the data, those events, will not have changed because it is immutable. So you have a conversation with someone and you speaking something and they say something and they say something. Those are events back and forth and they're happening over time. And just as if you have an argument with someone and you say something in heat and you say something you really didn't mean to, and kind of like the next morning you regret it a little bit, it's immutable. That has been said, those words were uttered. You can't go back and unsay those. And it's the same with an event log. Events happen over time. They are append only. They are appended to the end of the log. It is immutable. And if you put something onto it that you didn't mean to, well, you can kind of like counteract it and put another event in place. And in the kind of the analogy of the conversation, go and say sorry, but that original event still happened. It is immutable. So we can use this when we're building our systems because you have that guarantee that the data we read from that event log has not changed. Those events are as they occurred. So the events get added to the end of the log. It's immutable, it's append only, it continues over time. And that's the conceptual heart of Apache Kafka as an event streaming platform. So event streaming platform sounds big and fancy and kind of like a bit markety, but that's going to describe what we're going to build up around all of this fairly simple concept at the very heart of it, which is an immutable append-only commit log. And it's also distributed, by the way, which makes it very scalable and resilient. We'll talk about that later. But a log itself is a bit conceptual. And we need to actually work with this. We need to kind of have APIs, and we need to have a way of structuring the data. So we're going to carve up that log into what are called topics. And topics, if you're from a database background like I am, they're kind of like tables. And it's kind of like it's entities of data. So you have a topic which describes click events over time. So people click on your website, it gets appended to the end of that topic. They place an order, that event gets appended to the end of the orders topic. There's also a topic here for customers. And whilst streams of facts, like clicks or orders, are kind of like nice and easy to conceptually understand, like these things can happen continually over time, you can also use topics, you can also use events to describe reference information, lookup data. Because if you think about that itself, it's also created as an event. So a customer joins our organization, or they kind of like they sign up. That's a create event, and it's got information about their name and their email address, and then they change their email address. Well, that's another event. They change their email address, and now we have additional information about that customer. And if you keep all of that information about that customer on that particular topic, that series of events, you can now replay that and build up a full picture of the state about your customers. But you also now have more information than simply the state alone, because you can go back and say, well, when did they change their email address? How many times have they done this? So by capturing events, we can roll up to kind of like our normal view of data, like we would see in a relational database. But we also have the raw events that created it, which are also useful in themselves. These topics are how we're going to organize our data. But because Kafka is a distributed system, and because we want it to be scalable, we're also going to carve up these topics one more time. And we're going to carve these up into partitions. Partitions exist within a topic, and you can have one and usually more than one partition. And partitions are our unit of scale. And within a partition, we have our second really strong guarantee that Kafka gives us, which is that messages will be ordered within a partition within a topic. So a topic has 4 partitions. Within those 4 partitions, within each partition, you're guaranteed that the order in which the data was written to that partition is the order in which it will be read from that partition. So in the example of a customer, if you start reading from the partition, you're not going to get they changed their email address before you got the, oh, they got created event. So you have that strong ordering guarantee within partitions. Now let's see how we actually get the data in and out of these topics, out of this distributed commit log. Kafka itself has characteristics of a message queue. It's not just a message queue as you would think of like any other message queue on the shelf and like, oh, well, eeny, meeny, miny, we'll use Kafka here. It's just a message queue. Kafka has characteristics of a message queue. It's not just that. It's not just transient messaging, but it lets us do pod sub. Lets us put data onto it and take data off it with one or more different subscribers. So to get data on to a topic in Kafka, we use a producer. And the producer writes data to the end of the log. Just like we said, it's an append-only log. So something happens, we write it to the log. The producer will decide which partition are we going to write it to. There are producer API libraries for lots of different languages. There's Java, there's Go, like you can see here, there's Python, there's C, C++. any number of languages. If you can't find one for your language of preference, there's also a REST proxy, so you can just use REST calls to put data onto topics in Kafka. We said earlier about our events are going to be key value pairs, and this is where the key comes in. If you don't assign a key to your message, and you don't have to, Kafka will simply round robin distribute messages as they arrive across the partitions within a topic. So you get a nice even distribution of messages. But if you care about the partition to which data is going to get assigned, so you want messages for a particular customer or a particular business unit always to be in a particular partition, you're going to want to set a key on those messages so that then messages for a given key will always end up on the same partition. Now, you don't need the same number of partitions as the same number of key instances. If you have 10,000 customers, you don't need 10,000 partitions. You could have 2 partitions, and each partition is going to get 5,000 customers on it. But the important point is each customer will be on the same partition. So when we're reading the data from that partition, we're guaranteed that the data for the particular customer we're reading, any more data related to that customer will be on that same partition. So producers send data to topics. It's a client application that we write in any number of different languages. There's also a REST proxy. The producer API handles like talking to the brokers and working out which partition the data is going to go onto. And as I say, there's a REST proxy or lots of different languages we can use as well. To get data out of a topic, the subscribers, we're going to use the consumer API. So when we consume data from a topic, it's sequential access. So you can't do like random access and just scan through this whole thing or go through it and look for a particular type of a message or something like that. We say we're going to go to a particular topic. We can read data from the beginning of the topic, the end of the topic, or indeed any point within it, a particular offset or a particular timestamp. And we go to that point and we read those messages through. Now, Kafka itself doesn't delete messages when they get read. Kafka itself will delete messages from a topic when you've told it to. So you say to Kafka, on this particular topic here, I would like to keep the messages based on time. I'd like to keep them for 7 days for the orders, or 7 years for the customer information, or indeed you say, I would like to keep this data forever. So Kafka will delete the messages when you tell it to based on each topic settings. When consumers read the data from a topic, the data does not get deleted. The two concepts are completely separate. So we read data from a topic, the data stays on that topic. All that changes is Kafka says, okay, you got to this particular point in the topic here, and you said you've processed those messages. Kafka keeps a note of that offset. So when you come along again and connect and say, I'd like the messages, it says, well, you got to hear from last time, so now you get any new messages that have arrived since then. And because messages don't get deleted off the topic when they're being consumed, it means that other consumers can come along and they can say, I would like to read messages actually from earlier on in the log. I would like to reprocess everything that's happened. And this can be really useful because it means that we can write data to a Kafka topic based on a particular requirement. Like we need to capture order information into a topic to drive this particular application over here. And then someone else comes along after this initial application is launched and they say, oh, you've got order information on a topic. That's really useful. I would also like to use that. So then another consumer can come along without having to be declared up front or anything like that. And they say, oh, the orders topic, brilliant. Well, I've not processed any of them yet. So I'll go back to the beginning of the topic and I'll read all of those. And now I'm caught up and I can keep on processing them. And someone else can come along and say, well, I processed those ones, then I made a bit of a mistake. So actually, I'm going to rewind my offset back an hour or so until I made the mistake in my application. And I'm going to reprocess just those particular messages. Consumers are independent of each other. Consumers can seek back and forth in the log to read the messages that they want to. And Kafka will track where each consumer has got to. Again, lots of different libraries available. Here's an example using Go, where it will subscribe to a particular topic and process the messages as they arrive. Now, consumers, if you have a single instance of a consumer, will read data from every partition because you want to make sure you're processing all of the data. So without a key, the data is distributed across all partitions. The consumer will simply read the data from all of those partitions and process all of your data. You can have a second consumer, as we said, and that will also read all of the data from all of the partitions because these are two separate logical applications. One application is processing orders to kind of like to check for fraud. One of them is processing them to check for like scoring certain characteristics or some other purpose. Two separate applications. Now our first application here, C1, the blue box at the top there, we say, well, it's doing fraud processing and we need to increase the rate at which it's processing those messages. And we've scaled the box and we've put more CPUs in and we've done like special dances standing on one leg. It still can't process the messages at the rate at which we need to meet our SLA. So you say, well, that's fine. We can scale our particular consumers horizontally. We can add in additional instances of that application. So C2 at the bottom there is kind of like out of the picture. This is just like, it just keeps on doing what it was doing. But C1, the blue one at the top, we have now added in additional instances of that application. And what Kafka will do is it will say, great, we've now got what's called a consumer group. And it will say each of those instances of the application will get data from one or more partitions. So if you have 4 partitions and 4 instances of your consumers, then each consumer gets 1 partition. If you had 2 instances of the application, each instance will get 2 partitions, and so on. And Kafka keeps track of how many instances you have. So if you have 1 and you scale it up, it will rebalance. If you have 4 and you lose 1, it will also rebalance. It will say, well, that partition 4 at the bottom there, it was getting consumed by that particular instance, but we've lost that one. So actually I'll rebalance it now and one of the other instances will take over. So consumers, again, client application, reads messages from topics. We can scale it horizontally as we need to. And as before, lots of different client libraries available, also a REST proxy. We need somewhere for all this data to actually reside. We need a thing that's going to run these bits and bytes, a process that we can look at and poke and make sure it's actually doing what we want it to. And this is called the Kafka broker. We've talked about the events, we've built them into a log, we've split that up into topics. We talked about the APIs to getting the data in and out. But how do you actually run this thing? Well, what we run is called a broker. It's a JVM process, and we run 1 or more of them. Usually 3. It's a distributed system. We want to have redundancy. We want it not to want it to be able to form quorum, work out who's in charge and stuff like that. So we start off usually with 3 brokers, and we can scale it out as we need to for capacity and redundancy requirements. Because we have partitions, these get distributed across those brokers, and each broker will be the leader for a particular partition. So if you have 4 partitions and 3 brokers, one of those brokers is going to be the leader for 2 of the partitions. But we also have what are called follower partitions spread out across the other brokers. So each topic you can set what's called a replication factor and say, I would like to have 2 replicas or 3 replicas or however many replicas you need, and they'll get spread out across the brokers that you have. And because we have redundant copies of the data, it means that if we lose a broker, so we lose broker 3 here in a puff of smoke, then the other brokers have got that data also, and so can take over responsibility for being the leader of that partition. So this is kind of neat. This is building up the concept of an event streaming platform. This is talking about events that can then be in event streams and unbounded event streams that we can process in a scalable, distributed way. But we're only actually really getting going. This is just the foundations for a platform on which we can build some really powerful applications. And what people do with Kafka varies. Sometimes they build out these streaming pipelines, sometimes they use them to build event-driven applications, or sometimes they do both, and they kind of like, it acts as a central nervous system of their organization. But let's think about building a streaming pipeline. You say, I've got data in a database. I'd like to use Kafka to stream that over to somewhere else. We want to do analysis, stick the data into S3. Well, we've got the data in Kafka, so we could also put it into HDFS. So you think, well, we're going to have to write some code to get that data from the database into Kafka. We're going to have to write some code to push it into S3. We're going to have to write some code to put it into HDFS. Looks like a bit of Java we need here, maybe a bit of Spark, maybe something else. Or we say, well, never mind pipelines. We've got an application that we're going to build, and that application is going to be driven by events happening in a database, because in that database, we capture what's happening in like an existing application. So you can actually link them together using this. But again, data in a database, how are we going to get that into Kafka? I know, I'll write myself some code. Now, as Admiral Blackbow would tell us, this is all a trap. because writing code to do integration between systems into Kafka and from Kafka down to other systems, it kind of sounds like fun. Because we've got databases, we've got message queues, we've got event stores, and all of these different things we want to integrate into Kafka. So we start off and we say, well, here's the producer API, we'll write some code to get the data into Kafka, and here's the consumer API, so we'll write some code to get data from Kafka and push it to S3. And then we say, well, as well as S3, we need to get the data somewhere else. So why don't we make it pluggable? And actually, we need it to go kind of like to have high throughput, so we'll make it distributed. And we need to handle things like schemas and restarts and offsets and all this kind of stuff. This is great. We could like build ourselves a framework. We could do all of this stuff. Well, the problem is that's like entry, that's kind of like base requirements. Everyone needs to get data between Kafka and a database. Everyone needs to get data between Kafka and S3. So if you spend your time writing code to doing that, you're not actually differentiating your business. You're not solving any real problems that everyone else hasn't done already. And this is why Kafka provides an integration API for you. Kafka has solved this problem, which sounds like a lot of fun to solve, but it's been solved already. So in terms of wheels to reinvent, don't reinvent this one. Use Kafka Connect when you need to get data between systems upstream into Kafka, from Kafka downstream to other systems. So you can use Kafka Connect to do this, and it's just configuration file based. So you say, I want to use this connector, and I want to get data from here, and I want to write it to here. It's a pluggable architecture. So you say, I've got my particular connector for the particular technology I want to integrate with. I've got a converter, which is like my SERDES for serializing and deserializing as appropriate. We can even apply transformations. It's an open API. It's part of Apache Kafka. So if you're desperate to write some code and you find a system for which there isn't an existing connector, you can go and write some code. Yay, rejoice. Most of the time, you don't need to. Most of the time, the connectors will already exist. So you can head over to Confluent Hub and type in the particular technology with which you want to integrate, and it'll list out the different connectors that are available. I mentioned SERDES a moment ago. I mentioned serializing and deserializing data. And it's time now to think about what's within this little box of key value bytes. We've talked about how we're going to store them. We're going to store them on a log, within topics, on brokers. But what are these bytes? And talking about Kafka Connect and integrating with other systems actually starts us down the road of thought of, well, how are we going to do this in a way which is going to be resilient to changes, which is going to let us evolve rapidly, but without tightly coupling things together. So within this log of key value bytes, what actually is this thing? Well, hopefully it's not this. Hopefully it's not kind of like, well, I can eyeball it and I guess it's tab separated, maybe comma separated, maybe white space separated. And what are the different field names? And what are the data types? And are there any fields missing? I don't know. Are there any defaults? I don't know. And this is the problem if we don't think about how we're serializing our data. Because we say, well, I've got this new application to write. I'm going to use this fancy thing called Kafka. It's all good. I'm going to serialize the data using whichever thing I'm most familiar with, or whichever's quickest to get work, whichever one I found on Stack Overflow, and off we go. And then someone gets this payload, and they're like, well, what's this? And now this beautiful idea that Kafka enables of loosely coupling systems, of one team saying, I produce data onto a topic, and one or more other teams saying, I build applications that read data from that topic, in a nicely loosely coupled way, goes out the window. Because those people consuming the data have to phone up or email or whatever the people writing the data and say, well, what on earth is this? And what are these fields? And then in a couple of weeks, well, my consumers just stopped working. What did you change? Oh, well, I changed this thing. I didn't realize that anyone was using it. So thinking about schemas, thinking about serialization is really important because they're completely intertwined. So there are different ways to serialize your data. If you want to make life easy for yourself in the long run, please use something with support for schemas. So something like Avro, something like Protobuf, something like JSON schema, they let you take the schema from your data. And by the way, most data has a schema. It's just sometimes we choose to ignore the fact because it's easier, but it's not easier in the long run. It just lets us kind of brush it under the carpet and worry about it later. So you've got a schema in your data most of the time. If you use Avro, Protobuf, JSON schema, you can actually take that schema and it'll get put into the schema registry. So Confluent schema registry, community license, part of Confluent platform. You can then have the schema in there, you produce your data into there, and then consumers can come along and they can read that data from the schema registry to pull the schema down and deserialize the data, and they have the schema available. So I'm going to show you a demo at the end, time permitting, and I'll show you exactly how useful that is. The schema registry provides serializers and deserializers. Those serializers actually let you enforce compatibility guarantees. So you can't just decide to change the schema without actually making sure you're not going to break things for other people. So it's a hugely good idea. Let's finish our little tour of the ecosystem by thinking about the kind of applications that we build when we're consuming data. Now, within these particular consumers, there's a fairly standard set of patterns that we do when it comes to stream processing. We want to read the data, and we've maybe got data from like a factory, and we're getting information about the widgets being produced. And within these widgets set of data, there's only so many things, if you boil it down to the bare basics, that you're actually doing with the data. One of them, like in an example here, would be filtering that data. So you have a series of events arriving over time, unbounded, and you say, within that stream of data, I would like to filter it. I would like to say, as these events arrive, some of the events are about yellow widgets, some of them are red widgets. When a red widget arrives on this unbounded event stream, I would like to write it to a separate stream of data, because I've got an application in my business that needs to be driven by red events, red widgets only. So when a red widget occurs, my application wants to know about it, so I'd like to filter this inbound stream and route any red widgets to another stream. Apache Kafka has got a stream processing API. It's called Kafka Streams, and it's a Java library. So if you're writing Java applications, you pull in this particular library, and now you can do stream processing within your applications. So the idea here is that instead of building and provisioning and watering and maintaining a separate stack of technology and machines to do your stream processing jobs, you actually just build your applications as you did before, but now they're stream processing applications. So you do your stream processing within your existing applications. So you build them, you code them, you test them, you deploy them exactly the same way as your normal applications. Not everyone codes Java. Not everyone necessarily wants to be doing so. So in this case, you can use SQL, using ksqlDB to actually declare what you want to do with your stream processing. So here we can say, I want to create a separate stream, and you actually just declare, using SQL, how you want to process that data. Create a new stream, populated by the output of this particular select statement. So using ksqlDB, which again, it's Confluent community license, it's part of Confluent platform, it's actually built on top of Kafka Streams. And you can do all of these sorts of different things, but using SQL. So we can say, I'd like to filter the data. If the data matches this particular condition, then write it out to a new stream. I'd like to build a stateful aggregation. So start counting these things up, grouped by this thing, or do another stateful aggregation, but apply a predicate. One of the other very common patterns of streaming data is to say, well, we've done those things, or we may be doing one of those particular things. What we also want to do is we want to route that data to somewhere else, because we're going to do some ad hoc analytics, we want to do some machine learning on that data. So here we can use Kafka Connect with ksqlDB as a wrapper around it to say, as this data arrives, maybe we can like cleanse it or tidy it up a little bit, but we then take that data and we just write it to somewhere else. Right, let me show you a bit of an example of this in action, and then we'll wrap up, and if time allows, we'll do some questions. If not, we'll head over to Slack and we can do them over there. So the demo I'm going to show you is this one here, and it comes from, I'll show you this, from the Confluent demo scene repository. So demo scene repository has got a ton of different demos, and they're all based around Docker and Docker Compose. So the cool thing is, if you see something that sounds interesting, you can say, well, I've got Docker Compose, pull down the code, Docker Compose up, and then you can just follow it through and try it out. So this is the one I'm showing you here. I've got a little cheat sheet because I can never remember all of these things and not fat finger them when I'm typing them live. But you can actually take this and you can run it for yourself at home and try it out. So if I do this and do this, we're going to just check that everything's up first. Okay, so this is ksqlDB. So I'm going to show you an example of ksqlDB taking some data. So if I say show topics, we're going to have a look at the topics that we've got on my cluster, I've got a topic called trades. So what ksqlDB can do, as well as like all the SQL stuff, which I'll show you, it can also act as simply producer and consumer. So if I say print trades, it's going to act as a consumer and simply go to the topic and say, what's the data in this topic? Now we've got a bunch of stock trade data arriving continually. If I pause the output, you can see it's got a key and it's got a value. It's got like, was it a buy or sell, the quantity, the symbol, and so on. But this is just acting as a consumer, dumping it to the console, which is kind of useful. It's actually worked out how the data's been serialized. Now we're going to say, well, let's declare ourselves a stream. And a stream in ksqlDB is a Kafka topic. It's all simply a Kafka topic, but with a schema. I talked about schemas earlier, and we see now why thinking about how we serialize data when we write it to Kafka is so important. Because as a user of that data, I've come along to the cluster, I've been authorized to do so, I can access the data. Now I say, I've got a stream of data called trades, and I can say create stream against it. I can say describe that stream that you've just created. It says, well, here's the schema. So I've not had to go along to the person who wrote that data and say, well, okay, so you used JSON, I can eyeball it. I've guessed that these are the data types, is that right? I've guessed that there aren't any fields missing. Because they used Avro, there's actually an explicit schema being declared. So my consuming application, which in this case is ksqlDB, can go to the schema registry and pull down the schema. But it would also work with just like a native consumer application or Kafka Connect, pulls down the schema, and now people can use it. And because we have a schema, we can actually do projections within that data and apply predicates. So we can say select the side and the quantity from trades where the symbol is this. So now it's processing that stream of data as it arrives. And we could also have told it to go back to the beginning of the topic and process all of the data in the topic. This is just processing the data in the topic as it arrives now, and it's applying that filter. It writes out to the screen because this is a select statement. If I say create stream test as, so create stream is going to actually create a Kafka topic and write the results of this select to that Kafka topic. So we've created that, and I can say print, actually show topics. Oh dear, that's always fun in live demos when it does that. It's not done that usually. Let's give it a sec to see if it's going to behave. Show topics. There we go. So we've got a topic called test, and I can say print test, and now it's saying here are the messages arriving on that topic. So it's running a consumer against it. So we've taken an inbound topic, we've said pick out these particular fields where it matches this particular condition in the data and write it out to a new topic, and it's just a Kafka topic. So we can have other applications consuming from that data, from that topic if they wanted to. We can also do other things with this data. We can say, well, we've got all this information about these trades arriving. I would like to aggregate that data and write it to a database. We're going to do some reporting from the database, but we want to pre-aggregate it for performance reasons before we write it to the database. So we can do this. We can build ourselves what's called a table in ksqlDB. And a table is much more like a relational database table. It's key value state. So here we're saying create a table. We're going to do select the side. So is it a buy or sell? We're going to count up the trades and the total value where the symbol is this. And we do that. So now we've created that query. If I say show tables, we've now got a table called that. I can say select star from that table. And if we say emit changes, we can see what's happening in it, emit changes. And what I did up here was I said set offset to the earliest. So here I said when you build that table, go and process all of the data in that topic. So you can see here, like ksqlDB is basically acting as a consumer, just like a few levels of abstraction up. But the consumer can just go back and forth in the topic as it wants to. We can process from the end. We can say, actually, now I want to process from the beginning. So we've created that table, and now we're selecting from that table. So you've got your row key here, which is the buy and sell. We're doing a windowed aggregation. So we're saying break it down by 15 minutes. So every 15 minutes, tell me how many trades have there been, what's the total value, and so on. And the timestamp here is the Unix epoch. So you'll have to take my word for it. They are 15-minute windows. We'll see in a moment proper proof of that. And you can see it's continually updating because as trades arrive that match the predicate, the aggregate changes. And so the aggregate re-emits its value. But ksqlDB is maintaining that aggregate itself in memory. It's done in a distributed way, so you can scale out ksqlDB. And it's also persisted down to Kafka in the background as well. So if you lose a node, it can rebuild that state. It's kind of clever. But now let's take that aggregate that we've built and we're maintaining within ksqlDB, and let's push it down to a database. So here's Kafka Connect, using ksqlDB as a wrap around it. Create a connector using the JDBC sync connector. Go push it over to Postgres. So we're going to do that. Create connector, show connectors, make sure it's working, and it says it is. And if I come out of ksqlDB and head into Postgres, okay, so another SQL command prompt, but it's Postgres this time. If I say select everything from this table, you can see we've now got that data in Postgres. So we're not doing any aggregates here. We're just saying select everything from here with an order by clause. And you can see here's our time windows. So this is this must be UTC. So on BST over here, this is UTC on the server that it's showing. So 8:30 here is the most recent time window, and that 8:30 time window is still open. Okay, it started like 6 minutes ago. And if I rerun this query, I'm pretty sure in the source topic, new messages will have arrived matching the predicate. Therefore, in ksqlDB, the aggregate will have updated, which means it will be pushed over to the database. So if I requery it, if we look at these values here, we're going to expect them to change when I requery it. So we select that, and we can see those have changed because the source aggregate has changed, so it's updated it in place in the database. So what we've built out here is a topic of data being populated from somewhere. It could be from Kafka Connect pulling in from another database or a message queue. It could be a producing application streaming it into a Kafka topic. It could be anywhere. Like most systems nowadays integrate with Kafka. Data arriving in a Kafka topic. We've written a few lines of SQL to say, we'll take this data, filter it, and aggregate it. And then another SQL statement say, take that aggregate and push it down continually to this particular place, which here is a database. It could be Elasticsearch, it could be Snowflake, it could be anywhere else that we want to. So that is a brief tour of the Kafka ecosystem. We started off with the concept of an event, very, very abstract. These events are happening all around us. They model what happens in our businesses. And we said, well, let's call it a key value pair. It's just information and it's got a key. We're going to capture it in an append only immutable distributed commit log. And that log sits at the heart of Apache Kafka. We've got producer and consumer APIs for getting data in and out. And we've got the Kafka Connect API for doing integration between systems upstream into Kafka and from Kafka downstream to other systems, and doing so in a streaming fashion that's also distributed and resilient. And we can do stream processing using the Kafka Streams API. And this is all part of Apache Kafka. We then talked about some of the other pieces of the puzzle of the broader ecosystem. So in Confluent Platform, we add in the community licensed schema registry, the community licensed ksqlDB, also for doing stream processing. So if you want to learn more about Kafka and some of the concepts around all of this, you can go to that QR code, you can go to the URL there, download these books for free. If you're interested in the concept of a distributed commit log, the iHeart Logs book is particularly interesting. It goes into like, why is this so important? It's such a simple concept, but it powers so many important things. And then to learn more about Kafka, head over to developer.confluent.io. And here you can find a whole bunch of tutorials to take you through lots of different concepts. There's podcasts, there's videos, there's a whole bunch more. So with that, thank you very much for your time, and have a great day.